Welcome to our comprehensive guide on periodic properties and their variations, tailored for ICSE Class 10 Chemistry. In this video, we'll explore how the elements are arranged in the periodic table and how their physical and chemical properties change across periods and down groups. Understanding these trends is crucial for mastering chemistry concepts and solving related problems. Let's begin by revisiting the structure of the modern periodic table and why it's such a powerful tool for chemists. As we progress, you'll see how these patterns help predict the behavior of elements in various reactions. Modern periodic table is organized based on increasing atomic number, which reflects the number of protons in an atom's nucleus. Elements are arranged in rows called periods and columns known as groups or families. This systematic arrangement allows us to observe repeating patterns or periodicity in the properties of elements. The table is divided into metals, nonmetals, and metalloids, each with distinct characteristics. Understanding the layout of the periodic table is the first step in grasping how and why properties change in a predictable manner. Periodic properties are characteristics of elements that show a recurring trend when you move across a period or down a group in the periodic table. These include atomic radius, ionization energy, electron affinity, electronegativity, and metallic or nonmetallic character. By studying these properties, we can predict how an element will react chemically and what physical state it might have under certain conditions. Let's take a closer look at each of these properties and see how they vary across the table. Atomic radius refers to the size of an atom, typically measured from the nucleus to the outermost electron shell. As you move from left to right across a period, the atomic radius decreases. This is because the number of protons increases, pulling electrons closer to the nucleus. However, as you move down a group, the atomic radius increases due to the addition of new electron shells. This trend is fundamental in understanding the reactivity and bonding of elements. Ionization energy is the energy required to remove an electron from a gaseous atom. This property increases as you move from left to right across a period, because the atoms hold their electrons more tightly due to increased nuclear charge. Conversely, ionization energy decreases down a group since the outer electrons are farther from the nucleus and more easily removed. These trends help explain why some elements are more reactive than others, especially among metals and nonmetals. Electron affinity measures the energy change when an atom gains an electron. Generally, electron affinity becomes more negative across a period, indicating a greater tendency to accept electrons. Down a group, electron affinity becomes less negative, as added electron shells reduce the attraction between the nucleus and incoming electrons. This property is particularly important for understanding the behavior of nonmetals, which often gain electrons during chemical reaction. Electronegativity is a measure of an atom's ability to attract shared electrons in a chemical bond. This property increases across a period, reaching its peak with fluorine, the most electronegative element. Down a group, electronegativity decreases as the atomic radius increases, making it harder for the nucleus to attract bonding electrons. Electronegativity differences between elements help predict the type of bond, ionic or covalent, that will form. Metallic character of elements refers to how easily they lose electrons to form positive ions. Metallic character decreases across a period and increases down a group. Nonmetallic character, on the other hand, increases across a period and decreases down a group. This explains why elements on the left of the table are metals, while those on the right are nonmetals. These trends are crucial for understanding the chemical behavior of different element groups. Physical properties such as melting point, boiling point, density, and electrical conductivity also show periodic trends. For example, melting and boiling points generally increase towards the center of a period and then decrease. Density tends to increase down a group as atoms become heavier. Understanding these variations helps in predicting the states and uses of elements in everyday life and industry. Chemical properties, such as reactivity with acids, bases, water, and other elements, also vary periodically. For instance, alkali metals become more reactive down the group, while halogens become less reactive. These trends are linked to the ease with which atoms lose or gain electrons, which is governed by the periodic properties we've discussed. Recognizing these patterns is key to understanding chemical reactions and predicting products. Group 1 elements known as alkali metals include lithium, sodium, potassium, and others. These metals are highly reactive, especially with water, and their reactivity increases as you move down the group. Alkali metals have low ionization energies and large atomic radii, making it easy for them to lose their single valence electron. Their physical properties such as softness and low melting points also follow predictable trends. Halogens found in group 17 include fluorine, chlorine, bromine, and iodine. These nonmetals are very reactive, with reactivity decreasing down the group. Halogens have high electronegativity and electron affinity, making them eager to gain electrons. Their physical states change from gases to solids as you move down the group, reflecting increasing atomic mass and van der Waals forces. Transition elements, located in the center of the periodic table, display unique properties. They often have variable oxidation states, form colored compounds, and are good conductors of heat and electricity. Unlike main group elements, their periodic trends are less pronounced, but they play a crucial role in industrial chemistry and catalysis. Understanding their properties helps explain their widespread use in alloys and electronic devices. Lanthanides and actinides are two rows placed below the main body of the periodic table. Lanthanides are known for their high magnetic and luminescent properties, while actinides include radioactive elements like uranium and thorium. These elements show less regular periodic trends due to their complex electron configurations, but their unique properties make them valuable in technology and energy production. Periodic law states that the properties of elements are a periodic function of their atomic numbers. This means that when elements are arranged by increasing atomic number, similar properties recur at regular intervals. This law is the foundation of the modern periodic table and explains why trends in properties are observed. It also helps chemists predict the discovery of new elements and their characteristics. Periodicity in properties allows scientists to classify elements and predict their behavior in chemical reactions. This systematic approach simplifies the study of chemistry, making it easier to understand complex reactions and the formation of compounds. The periodic table is not just a chart, it's a powerful tool that brings order and logic to the vast world of chemical elements. While the periodic table is arranged by atomic number, earlier versions used atomic mass. However, atomic number provides a more accurate organization, as it directly relates to the element's identity and properties. This shift resolved inconsistencies in the placement of certain elements and reinforced the periodic law. Understanding the difference between atomic number and atomic mass is essential for interpreting the table correctly. Valency refers to the combining capacity of an element, determined by the number of electrons in its outermost shell. Across a period, valency first increases and then decreases, while down a group, elements tend to have the same valency. This trend is crucial for predicting how elements form compounds and participate in chemical reactions. Oxidation state is the charge an atom would have if all bonds were ionic. Main group elements usually have fixed oxidation states, but transition elements can exhibit multiple states. This variation is due to the availability of d orbitals, allowing transition metals to form a variety of compounds. Understanding oxidation states is key to mastering redox reactions and complex ion formation. Nature of oxides formed by elements changes across a period. Metals on the left form basic oxides, metalloids in the center form amphoteric oxides, and nonmetals on the right form acidic oxides. This trend reflects the changing metallic and nonmetallic character of elements and is important for understanding environmental chemistry and industrial processes. Hydrides are compounds formed when elements react with hydrogen. The type of hydride formed, ionic, covalent, or metallic, varies across the periodic table. Alkali and alkaline earth metals form ionic hydrides while nonmetals form covalent hydrides. Transition metals can form metallic hydrides. These differences are linked to the element's position and its periodic properties. Solubility of compounds like salts and oxides varies periodically. For example, the solubility of alkali metal salts increases down the group, while that of alkaline earth metal salts decreases. These trends are influenced by lattice energy and hydration energy, both of which are related to the size and charge of ions. Understanding solubility trends is important for predicting precipitation reaction. Electropositive elements, mainly metals, tend to lose electrons and form positive ions. Electronegative elements, mainly nonmetals, tend to gain electrons. The degree of electropositivity decreases across a period and increases down a group, while electronegativity shows the opposite trend. These concepts are fundamental for understanding ionic and covalent bonding. Certain elements show similarities in properties diagonally across the periodic table, such as lithium and magnesium or beryllium and aluminum. This diagonal relationship arises due to similar charge densities and atomic sizes, despite being in different groups. Recognizing these patterns helps explain exceptions to general periodic trends. First element in each group often exhibits properties different from the rest of the group. For example, lithium, beryllium, and boron show unique behaviors due to their small size and high charge density. These anomalies are important for understanding the chemistry of these elements and their compounds. Type of chemical bonding, ionic, covalent, or metallic, varies across the periodic table. Metals on the left tend to form ionic bonds, nonmetals on the right form covalent bonds, and transition metals can exhibit metallic bonding. These trends are directly related to periodic properties like electronegativity and ionization energy. The acidity and basicity of oxides and hydroxides change across the periodic table. Basicity decreases and acidity increases across a period, while down a group, basicity increases and acidity decreases. These trends are important for understanding the behavior of elements in acid-base reactions and environmental chemistry. Reducing power, or the ability to donate electrons, increases down a group for metals, while oxidizing power, or the ability to accept electrons, increases up a group for nonmetals. These trends help explain the reactivity of alkali metals and halogens and are essential for understanding redox reactions. Many transition elements and their compounds exhibit vivid colors and magnetic properties. These trends are due to the presence of unpaired d electrons, which can absorb visible light and create magnetic moments. Understanding these properties is important for applications in pigments, magnets, and electronic devices. Transition metals have a strong tendency to form complex ions with ligands. This property is less common in main group elements. The ability to form complexes is linked to the availability of vacant d orbitals and variable oxidation states, making transition metals versatile in catalysis and biological systems. Many transition metals act as catalysts in chemical reactions due to their ability to change oxidation states and form complexes. This property is widely used in industrial processes, such as the Haber process for ammonia synthesis. Understanding periodic trends in catalysis helps in designing efficient chemical processes. Alloys are mixtures of metals that combine the properties of their components. The ability to form alloys depends on atomic size and electronic structure, both of which follow periodic trends. Transition metals are especially important in alloy formation, leading to materials with enhanced strength and durability. Corrosion is the gradual destruction of metals by chemical reactions with their environment. The tendency to corrode varies across the periodic table, with alkali and alkaline earth metals being more reactive and prone to corrosion. Understanding these trends is important for material selection and protection in engineering. Certain elements are essential for life, such as sodium, potassium, calcium, and iron. Their biological roles are linked to their periodic properties, such as ionic size and charge. For example, sodium and potassium ions are crucial for nerve function, while iron is vital for oxygen transport in blood. The environmental impact of elements and their compounds is influenced by periodic trends. For example, heavy metals like lead and mercury are toxic due to their position and properties, while elements like carbon and nitrogen are essential for ecosystems. Understanding these trends helps in managing pollution and promoting sustainability. Elements are chosen for industrial applications based on their periodic properties. For instance, aluminum is used for its light weight and resistance to corrosion, while copper is valued for its electrical conductivity. These choices are guided by a deep understanding of periodic trends and their practical implications. Periodic properties influence many aspects of our daily lives, from the batteries in our devices to the medicines we take. For example, lithium is used in rechargeable batteries due to its position in the periodic table, while iodine is essential for thyroid health. Recognizing these connections makes chemistry more relatable and relevant. Advancements in technology often rely on elements with specific periodic properties. Silicon, for example, is the backbone of the electronics industry due to its semiconducting properties, while rare earth elements are essential for high-performance magnets and screens. Understanding periodic trends enables innovation and progress in technology. Many medicines and diagnostic tools are based on elements and their compounds. For example, radioactive isotopes are used in imaging, while platinum compounds are used in cancer treatment. The choice of elements is guided by their periodic properties, such as reactivity and stability, ensuring safety and effectiveness. Elements like nitrogen, phosphorus, and potassium are essential nutrients for plants and are supplied through fertilizers. Their effectiveness and uptake by plants depend on their periodic properties, such as solubility and ionic form. Understanding these trends helps in developing efficient fertilizers and sustainable farming practices. Water treatment processes often use elements like chlorine and ozone to disinfect and purify water. The effectiveness of these elements is linked to their periodic properties, such as oxidizing power and solubility. Understanding these trends ensures safe and clean water for communities. Elements like uranium and thorium are used as fuels in nuclear reactors, while hydrogen is explored as a clean energy source. Their suitability is determined by periodic properties such as radioactivity and energy content. Understanding these trends is vital for developing sustainable energy solutions. Material science relies on the selection of elements with specific periodic properties to create new materials with desired characteristics. For example, superconductors and nanomaterials are developed using elements chosen for their unique trends in conductivity and reactivity. This field is at the forefront of innovation in technology and engineering. Sum up, periodic properties and their variations are central to understanding the behavior of elements in both physical and chemical contexts. By mastering these trends, you can predict reactions, choose materials for specific purposes, and appreciate the interconnectedness of chemistry with everyday life. The periodic table is more than a list, it's a map to the world of elements. Congratulations on reaching the end of our journey through periodic properties and their variations. With this knowledge, you're well equipped to tackle ICSE Class 10 chemistry questions and explore the fascinating world of elements. Remember, understanding periodic trends is not just about memorization, it's about seeing the logic and beauty in the organization of matter. Keep exploring and let the periodic table guide your curiosity.